Hello world, thanks for joining me today, and thanks to Codeland for having me. I'm going to share with you all some ideas about emoji encoding, Unicode, and internationalization. I'm Naomi Meyer, and I work as a software development engineer at Adobe on the Globalization team, where I do international engineering for Creative Cloud products. Here's where you can find me online. If there's anything you feel passionately about or have a strong opinion on, please let me know. I would love to continue the conversation online. So I'm sure most of us have seen this many times in the head tag of our HTML markup. We all know to add this meta char set equals UTF-8 line. But I've been fascinated lately about the underlying details of what this UTF-8 thing really means and does. So I'm really excited to share some more details about it and why I think it's so cool. Also, this connects with this JavaScript funniness that we can see here, where seemingly single character emojis, when as strings, have a length a lot longer than expected. Feel free to try it yourself in your dev tools. This is also related to emojis in Twitter taking up 2 characters and not 1. So part of my goal today is to talk about why this is and to provide some more details about the underlying encoding involved here. Speaking of emojis, I personally find them both delightful and intriguing from an engineering perspective, a linguistic, international, creative design perspective, and so much more. In terms of reach, emojis have more users than any other character set or language on Earth. So let's use some fun emojis. Overall, our agenda for today is to start with some definitions of internationalization or I-18N. Then we'll move to a bit of encoding history to understand more of where we came from. Then to the Unicode consortium and the UTF-8 algorithm. Finally, we'll talk about how this allows us to encode emojis and different languages across the World Wide Web. So, let's start with some definitions of internationalization. I think it helps to use an example to get your head in the internationalization mind space. So the string, hello, my name is Naomi Meyer. That's the common way we introduce ourselves in the United States in American English, where we use the first name, given name, followed by the last name, family name, surname, syntax. But if we translate this string into Hindi, Chinese, Japanese, Hebrew, Arabic, Korean, we can see that there's a significant variety across languages. Sometimes the order is first name, last name. Sometimes it flips and it's last name, first name. Sometimes the text is reading left to right. Sometimes the text reads right to left. And of course, there are different languages, there are different character sets, fonts, and so much more. So to enable our users to enter their names across a wide variety of languages across the world is part of what we're talking about with internationalization of software. Here's a paradigm we often talk about on my team, where we have the most granular level of translation, or T9N, where hello becomes hola, konnichiwa, bonjour. Then localization, or L10N. And as you can see, in the United States in American English, I'm spelling localization with a Z. But if I go across the pond to London in the UK, I would spell localization with an S. English as spoken in the UK. They're both English, but they're different regional dialects or locales of the same language. So the localization process includes that. Next, we have internationalization, or I-18N, and that's the engineering process of preparing an app or a website to be shipped with translations. And in internationalization, we take a hard-coded English string and wrap it in an I-18N object for translation. And these all kind of fall under the umbrella of globalization, or G11N. And globalization also includes non-engineering topics like legal, sales, marketing, but we're not going to get into those today. And these are numeric acronyms. So globalization, we take the first character G, followed by the number of characters, 11, and then the last character, N. I think there's another higher order component that these fall under, and that's accessibility and innovation, because culture is deeply rooted in our thinking patterns, and it affects how our users interact with and benefit from our digital experiences. So internationalization really goes way beyond translation, and by acknowledging cultural characteristics and celebrating differences, we're creating with innovation. So, with those definitions set, let's jump into encoding. Of course, when we're on our computers, tablets, and phones, when we type an emoji, a letter, a number, these are ultimately interpreted by the machine as zeros and ones. So let's get into a bit of the guts of how that works. But to understand where we are today, we have to jump back into history to see how we got here. So, this image is from 1963, the first version of the American Standard Code for Information Interchange, or ASCII, which encoded 128 English-only characters into 7-bit integers. Then, in the 1980s, we went from 7 bits to 8 bits. And because different languages and different locales have different accents or diacritics on their characters, they use a different encoding system for their unique computer systems. And that was fine. Different encoding systems worked independently until 1991, when the World Wide Web hit. And the internet kind of broke computers because there was no universal encoding system. And when two different non-compatible encoding systems encountered one another, we got a collision, something that looks like this, with a lot of question marks and garbled characters. So to solve this problem, enter Unicode. Unicode version 1 came out in 1991 and is still running today. So let's talk about Unicode. To understand Unicode, there's some definitions that we need to handle. And props to Dmitry Pavlutin for his great article talking about this. So first we have a code point is a number assigned to a single abstract character. For example, U plus 0041, where U is the prefix that means Unicode, and 0041 is the hexadecimal number. This code point represents the abstract character Latin capital letter A, rendered as the glyph A. So it's kind of like a phone book. If we look up U plus 0041 in Unicode, we get A. And Unicode defines over 1 million code points. And by having this one-to-one mapping, it helps to ensure that there are no collisions between different alphabets of different languages. But because there's over 1 million possible symbols, to help keep things organized, Unicode divides the range of code points into 17 equal planes. Not like airplanes, but like groups. Sorry, bad joke. And each of these 17 equal groups have 65,000 code points each. So here's one way to represent it, where we can see plane 0 is the basic multilingual plane in blue, and then all subsequent planes are the astral planes or supplementary planes. Here's another way of looking at that same thing, where we can see plane 0, the BMP is separate, it's different than the other planes. So let's talk about why. The BMP, or the basic multilingual plane, is the unification of all prior character sets. So here's what it looks like. We can see a breakdown where some are Latin script, but the vast majority of these characters are East Asian and Chinese, Japanese, and Korean scripts. I think it's so fascinating. So how does this relate to metachar set UTF-8? Well, let's kind of try and tie it all together here. So we know about code points and abstract characters. And we know those ultimately need to be interpreted by computers at the memory level into physical bits. So we need a way of translating from code point to code unit. The character encoding translation system is what will translate from Unicode to physical bits. And one of the popular open source algorithms for this is the Unicode Transformation Format, or UTF. And there are 3 popular encodings, UTF-8, 16, and 32. As we've discussed, UTF-8 is most common on the web. UTF-16 is used by Java and Windows, and 32 is used most by Linux and Unix systems. So here's a way to see the difference between 8, 16, and 32. And the beauty of UTF is that it's reversible. So conversions between all of them are algorithmically based, fast, and support lossless round tripping. So JavaScript is my favorite language. And I wanted to know which UTF is JavaScript. You know, if it's React, Angular, Vue, Svelte, whatever, which one is JavaScript? And the more I've dug into it, the wilder it is. So the ECMAScript standardized version of JavaScript defines how characters should be interpreted. And it states you can use either UCS2 or UTF-16. UCS2 is a 2-byte universal character set, and UTF-16 is a 16-bit Unicode transformation format. So these are 2 totally different contrasting systems, which creates all sorts of weirdness in JavaScript and Unicode bugs. So let's talk about some of them. First, we have the combining mark. So this modifies the preceding character. Here's an example of an A with a little circle over it in Danish, where we can see we use the Unicode character for A, followed by the combining mark with the ring above as the circle. And these are 2 separate Unicode characters. If we log them to the console, we can see that combined, they return A with a circle above it. Another example is cafe with an asterisk over the E. If we create this variable drink with cafe of an asterisk, we would assume that the length of this string would be 4. But because that final combining mark is an additional Unicode character, the length is 5. And then if we split it into an array, we get the final index of the array is the combining mark. So as I'm sure you can imagine, this creates a number of bugs and confusion for developers about strings that include Unicode characters. So one solution of many is to use string.prototype.normalize, which is native part of the JavaScript API. And this normalize method returns the Unicode normalization form of the string. Here's it working with cafe, where if we add the normalization method, we can see cafe is now a length of 4, and when we split it into an array, we don't get that final index with the accent. And this is good to avoid Unicode localization bugs. But unfortunately, there are a number of JavaScript libraries that deal with strings and fail to take into account these type of symbols properly. So it's good to look out for. It's also good to look out for I saw this tweet, and I think it's a good example, where there's a woman named Raquel Velez with an accent over the E in Spanish. And she is not able to enter her last name into a government form because this form is clearly not encoding Unicode characters correctly. So, use UTF-8, understand your encodings for good, and to build inclusive forms. So let's move on and talk about emoji in general. And we're using emojis as an example, but this same logic can apply to international languages and scripts to build inclusive web apps and forms. So it wasn't until Unicode version 6 in 2010, nearly 20 years after Unicode started, that they first added emoji. So all modern emoji live outside of the BMP in planes 1 through 16, in the astral planes or supplementary planes, which remember had 5 to 6 hexadecimal digits. So for example, we have the grinning face emoji, which is 1F600. So it's 5 hexadecimal digits, which take 21 bits to save in memory, therefore require 2 code units of 16 bits. So the way we can handle that is with a high surrogate and a low surrogate pair of code units to equal that one astral code point. So here's the code of how we can get the surrogate pair from the astral code point with the smiley face example. And because these are two separate Unicode characters, if we try and check the length of the smiley face, we see the length is 2. And if we try and split this string, we get these two garbled characters, which are the high surrogate and low surrogate pairs. Another good example is if we try and reverse a string with an emoji. Here we're trying to do string.split.reverse.join on the smiling poop emoji. And as we can see in red, the astral plane of surrogate pairs is returned as garbled characters instead of the poop emoji here. We can also see the combining mark example when we, the first line here with mañana, the N with a tilde over it is the character without the combining mark. So that is able to reverse correctly. But the second example, we have the N Unicode character plus the combining mark character with the tilde, and when we try and reverse that string, the tilde moves to, instead of over the N, over the A. This is obviously something that we really want to try and avoid. So Matthias Baynard suggests using the pile of poo test, where you include a pile of poo or a string similar to this internationalization string, which includes surrogate pair code points on the astral plane. Then you can check your code test for these unique use cases and make sure that nothing breaks. So speaking of pile of poo, let's talk about some special emojis. One special emoji is called the zero width joiner, or ZWJ. That's hard to say. And it's not an emoji itself, but it's used in emojis and language sequences as glue to attach different emoji code points together to create compound emoji sequences. Another special emoji set is the emoji skin tone modifier. And I was fascinated to learn that this is built on the Fitzpatrick scale, which is a dermatology scale based on UV light exposure. And these were added in Unicode 8.0. Another interesting special emoji is the variation selector 16, which takes a plain text representation of a character, and by adding variation selector 16 in red there, you can see that it stylizes it. So it adds style. That's why I like to think of it as the Pose emoji, because I love the TV show Pose and they're very stylish. So let's look at that all together. If we take the example that we looked at the very beginning, the singer, it's a combination of a number of emojis. So we have the female emoji plus this medium skin tone modifier plus the zero width joiner plus the microphone, which all combined make the singer emoji, and that's why the length is 7. Another example is this eye in speech bubble emoji, where we have the eye plus the style variation selector 16 plus zero width joiner plus left speech bubble equals eye in speech bubble, which just blows my mind and I find it fascinating. Emojis can be proposed. So this is an interesting proposal from last year. It's the proposal for consistent gender options for emoji zero width joiner sequences from Jennifer Daniel. And this is I think it's a really amazing addition. It was included in Unicode. And what it does is, instead of having a default male or female representing emoji, instead there is a human or person emoji displayed that's more non-binary. And then you can include a male or female component. So Jennifer Daniel talks about this in one of her talks, where she says, we took the mermaid, and remember here that emojis are like fonts. So they vary across different platforms. You know, on Apple, Google, Microsoft, you're going to get different font variations of emojis. So here's the mermaid emoji. Here's the merman emoji. And then the new addition is the merperson. And this came out in Emoji 12.1 in 2019. And I think it's great. Another new emoji was introduced by this teenager from Saudi Arabia who said, I want an emoji of me. And so she proposed a woman with headscarf emoji And it went through the process, and it's now included in Unicode on billions of devices. Another woman with Chinese heritage wanted a dumpling emoji and successfully got that through. So anyone can propose an emoji. And it's a long process, but it's possible. The link is right here. You can click it and follow the process. There's also an amazing documentary that talks about many of these emojis listed here that were proposed kind of externally, called Beyond the Emoji. And overall, I think it's super important to have more transparency about the process of how we take emoji and encode them into bits, and how we get new emojis included in Unicode and new languages. Because it's not just a matter of having the right icon to describe what you ate for lunch. It's about a digital acknowledgement of different cultures, of who gets to be represented in our future digital language. These representations matter. So please go out there, submit an emoji, encode your strings accurately, and put the world in the World Wide Web. Thank you so much. Let's continue the conversation online.